post-lab questions from the page 816 lab. Just going to go through them really quick to help you out. So number 1 said write a balanced equation for the reaction of baking soda and acetic acid. Be sure to include all the physical states of matter for the reactants in the products. So this was the classic vinegar baking soda reaction. So, and I'm going to color code these by anions are going to be red and cations are going to be blue. So first we had sodium bicarbonate, NaHCO3, and that was a solid. And we added that to some vinegar, which is CH3COOH. And hopefully remember that acids are aqueous. And this is going to make, this is at first glance is a double replacement reaction. So I'm just going to swap the red guys. And we are going to make first H2 CO3, also known as carbonic acid, which would be aqueous, but we're going to do something with this in just a second. And we're also going to make sodium acetate. And when you're writing organic polyatomic ions, which acetate is, the polyatomic ion actually goes first. It's kind of weird. And then the cation goes last. So it looks like that, but this is called sodium acetate. Now, I said I was going to come back to this. Oh, wait, hang on. We need to put this. This will also be aqueous. I said I was going to come back to this. This is carbonic acid. It does something kind of funky in that carbonic acid falls apart very quickly, and you can actually call it instantaneously, to make water and carbon dioxide gas that will bubble off. And that's the wow factor of the baking soda vinegar reaction, is that it bubbles off that CO2 and it, you know, foams up, fizzes, and yay, it's really cool. And so this is actually the correct balanced equation. The carbonic acid doesn't last long enough to actually be qualified as a product. These two are the real products. So then number 2 said use a periodic table, calculate the molar mass of each of the reactants and products. So doing that, all you got to do is add up the mass of sodium, hydrogen, carbon, plus 3 oxygens to find sodium bicarbonate, which is going to be 84.01 grams per mole. I'm just going to put this up here real quick because I know you guys know how to find this. For the acetic acid, it's going to be 60.06 grams per mole. Water, of course, is 18.02, and carbon dioxide is 44.01, both of these grams per mole. And then sodium acetate is 82.04 grams per mole. And then number 3 asks, explain what caused the bubbling. Bubbling is caused by the only gas that was made, that's CO2. Number 4, how do you know that all the residue is actually the sodium acetate and not a combination of the sodium acetate and the baking soda? Well, the reason that you know that is because we were real careful when we were mixing these guys to make sure that the sodium bicarbonate was the limiting reactant and the vinegar, the acetic acid, was the excess reactant. And in doing that, we make sure that all of this sodium bicarbonate has reacted, so that over here, when we evaporate off all the water, we know that the only thing that's left is the sodium acetate. We're also evaporating off all of the excess vinegar that was left over. So the only thing left is sodium acetate. Number 5, calculate the mass of NaHCO3. Well, it's not really a calculation because we measured it out. And in the online version of this, I used 2.53 grams. Here we go. 2.53. Oh, shucks, that's not it. Okay, sorry. 2.53 grams of our baking soda. And then it says to convert that to moles. So to convert this to moles, we just simply have to use that molar mass that we figured out up here And so 84.01 grams is equal to 1 mole. And that works out to something. I don't have a calculator. Give me just a minute. So 2.53 divided by 84.01 gives us 0.0301 moles of sodium bicarbonate. And then we had 2.17, I think is what it was, grams. This might not be the exact right number, but I know it's close. Of the sodium acetate, which is the next thing it says, find the mass of the sodium acetate. So that was what we had. By subtracting, it was like 112 point something minus 109 point something. So you ended up with like 2.17 grams of the sodium acetate. I'm just going to be lazy and call it sodium acetate because I don't feel like writing that out a whole bunch of times. Molar mass of this guy, 82.04 grams per mole. Again, I'm putting the grams on the bottom because whatever I have here, I want to have right here, so it'll cancel out. And so you end up here with 0.0258 moles of the sodium acetate. And then number 6, using the balanced equation and the amount of NaHCO3, determine the theoretical yield of the sodium acetate. So what that is asking me to do is to take this number right here and perform stoichiometry, because when you're asked to calculate a theoretical yield, that means take this number and convert it into a mass of this number. So that's what we're going to do right now. So I'm going to take that 2.53 grams of NaHCO3 and I'm going to convert it to grams of sodium acetate. So use my molar mass to get to moles. And then use my mole ratio to get from moles of NaHCO3 to moles of sodium acetate, and it's a 1-to-1 ratio. And again, I'm just abbreviating sodium acetate with this. And then molar mass to get to grams. And it was 82.04 grams. Wait. 84.02. No, 82.04. So then that means the math that I did on the other one where I put 84.02, I had a little bit of a dyslexic moment. It happens. And so now we'll just plug this in. Cross out what you can, because it's fun. And then I'm going to multiply 2.53 times 82.04 divided by 84.01. And I get 2.47 grams of sodium acetate. So this is what I expected to get. This is my theoretical yield. And basically what the theoretical yield is if everything in this reaction goes exactly right. And what that means is these guys line up exactly how they're supposed to line up to react. They hit each other with the right amount of force to react. Everything goes perfect. Then that means I should be able to make 2.47 grams of sodium acetate. But then on number 1, on conclusions, it asks what's the percent yield. Well, percent yield is where you get to factor in, well, everything didn't go perfect. You know, this is the real world. Things don't work out perfectly. And so the percent yield is the experimental result. So in our case, it was 2.17 divided by what you expected to get, the theoretical. And this is a percent yield, so we take this and multiply it by 100. So our experimental was 2.17. Our theoretical was, now that we've calculated it, 2.47. Take that, multiply it by 100, and it works out to 87.85%, or in correct sig figs, 87.9. Not too bad of a percent yield. It's, it's kind of low, but it's not too bad. And then number 2, what is the theoretical yield of CO2? So we're going to do this exact same thing, but at this point right here, when we convert from moles of sodium bicarbonate to moles of sodium acetate, we're actually going to convert this to moles of CO2. So I'm actually just going to erase this part. Whoopsie daisy. I don't want to erase that. Why is it erasing that? There we go. Erase that part. Get rid of that guy. Why is that going away? Sometimes technology works great and other times not so much. So at this point right here, and erase my answer, of course, because I don't want that on here anymore. Right here, where I converted from moles of sodium bicarbonate to moles of sodium acetate, instead I'm going to convert to moles of CO2. And everything's a 1-to-1 ratio, so I can just put 1 mole of CO2. And then for each mole of CO2, I have a molar mass of 44.01. And now I can cancel this out, and I'm left with grams of CO2. So my math looks a little different. So 2.53 times 44.01, and then divide that answer by 84.01, and you get 1.33 grams of CO2. Then the next part of that question says, using the density value given of 1.25 grams per liter, this is the density of CO2 gas at room temperature and 1 atmosphere pressure and yada, yada, yada. Calculate the volume of CO2 produced in this particular reaction. So we have grams and we have density. And density is one of those things that you can use to convert between grams, mass, and volume. So that's what I'm going to do next. And I'm actually going to show you a neat little trick. So I'm just going to erase this, our little answer here. And I'm going to take my stoichiometry setup. Whoops, I need to go back to the pen. And I'm just going to extend this out a little bit. And remember, whatever unit is in the top rightmost box, that's the unit that you are currently in. And so I can take this density right here, and if you think it looks like a conversion factor, it's because it does. And I can put this 1.25 grams, I got grams, I can put it right here on bottom, and that 1 liter on top. And so now I've converted my grams of CO2 into liters. So that's kind of a nice thing about density. So I can take that number that I just got, that 1.33, and divide it by 1.25, and I get my answer, 1.06 liters of CO2. So when I used this much sodium bicarbonate, I produced about a liter of CO2. And then number 3 asked how many moles of sodium bicarbonate are needed and how many moles of sodium acetate are produced if we make 425 mils of carbon dioxide. So this question is asking me to start at 425 milliliters of CO2. So I'm basically starting here at volume, and I'm going to work my way all the way back to mass. And so it's going to look just like this stoichiometry, but going the other direction. Now, the density right here is expressed as 1.25 grams per liter, and they just gave me my number in milliliters. So I've got to make this match, and there's 1 of 2 ways that you can do it. You can either add another box to your stoichiometry where you say that 1,000 milliliters equals 1 liter and put it in that way, or if you want, and this is what I do, I know that I can just kick my decimal back to the left 3 places when I'm going from milliliters to liters. So I go 1, 2, 3, and so it's 0.425 liters of CO2. So that's actually where I'm going to start. I'm going to erase all this, and I'm going to show you that it is pretty much going to be the exact opposite of this guy whenever you're going to sodium acetate, which is what we're going to do first. So I'm going to take my 0.425 liters of CO2. And in order to get from CO2 back to sodium acetate, I know that I have to use my mole ratio. Well, I can't go from liters to moles, at least not yet. I haven't taught you guys how to go deal with gases and moles and whatnot. That'll come next chapter. But I can use my density to get from liters to grams, and then we know how to get to moles. So I'm going to use this conversion factor, this density, as it is, since it's got liters on the bottom. So for every 1 liter of CO2, we have 1.25 grams. And now I convert from grams to moles using my molar mass, 44.01 grams of CO2 for every mole. So I've done this step, and now I'm at the mole ratio step. So for every mole of CO2, I'm going to need a mole of sodium bicarbonate. And now I need to get to mass. So I use my molar mass again. So for every mole of sodium bicarbonate, I'm going to have 84.01 grams sodium bicarbonate. So I have a lot of numbers going on here. So what I'm going to do is I'm going to multiply all the way across the top, and then I'll divide by what's on the bottom. So 0.425 times 1.25 times 84.01, and that's equal to 44.6. Now I'm going to divide that by 44.01 equals, and I get 1.01 grams of sodium bicarbonate. So that's the first part of the question, and then they wanted to know how many, the question asked how many moles. So you know what? I didn't have to do this last step. I could have stopped right there. And I would have gotten 84.01, 0.0121 moles of that stuff. So careful to read the questions, because I went one step farther than I needed to. So the question was how many moles, so that means I didn't need this whole entire step. Now the other thing was how many moles of sodium acetate. Well, everything in this equation is a 1-to-1 ratio. So if I need 0.0121 moles of sodium bicarbonate to make this much carbon dioxide, well, since it's a 1-to-1 ratio, then I'm also going to make 0.0121 moles of the sodium acetate along with it. Now, that is all the questions that I asked you guys to be able to do. And if you have any more questions, you know where to find me.